We are Group 39 here with our project on C++ code vulnerability detection system using large language model fine-tune. These are our group members. So what is the challenge with C++ security? There is a high risk in C++ that is prone to critical memory-related vulnerabilities like buffer overflows, which will lead to severe system compromises. And also, the traditional static analysis tools often have high rates of false positives and also lack the contextual explanations that are needed to educate the developers regarding the issues. So what we need is a more intelligent tool that is required not only to detect the flaws, but also to help the developers to understand and also fix them, which improves the secure coding practices. Our solution is an AI-powered system which we named SafeC. Here, the core technology is a fine-tuned LLM, which is Pen3, having 4 billion parameters, specifically trained to identify and explain the security vulnerabilities in C or C++ code. This is a developer-centric integration because we have used this model on a VS Code extension so that it reduces the time and expertise needed for security code reviews by offering fast, accurate, and educational analysis for the developers.
So our final product is the SafeC VS Code extension, which is capable of analyzing and identifying security vulnerabilities in C or C++ code. So here you can configure the SafeC into settings like giving the API host, where model is hosted. Currently the model is hosted on an EC2 server, and here's the API port which is exposed to internet. Then the model name. This is actually the fine-tuned model we saved. We have saved. We use the Quen3 4 billion parameter model and fine-tuned it using our custom dataset. So here you can configure the SafeC to use those things. Then just right-click and we can analyze the C code for vulnerabilities. So here you can see the report is generating. So actually this test function is, this system demo function has a classical buffer overflow vulnerability. So this is actually identified by our model CWE126, which is the common vulnerability enumeration given by the community. And here you can see the common consequences and description of the identified vulnerability. Like this, the system can identify the vulnerabilities in the C code. Actually, this is capable of identifying multiple vulnerabilities in a code. So here is the system architecture for our fine-tuned models. So first of all, we have data processing layer, and then we have model training layer, then the deployment layer, then the application layer. So first, data processing layer, we use Juliet test dataset. Actually, we researched about datasets and found the Juliet dataset as the best fit for our C and C++ code vulnerability project. Actually, the Juliet dataset contains this kind of file system, and they have the CW enumeration based codes, and here are the codes. And so we have to pre-process the data set, and we did the pre-processing in 6-stage pipeline, and we created a balanced data set, and then we stored it in the Hugging Face hub. So after we come into model training layer, so as our base model, we use Quen3 4 billion parameter model. Actually, we use several models, and with fine tuning, here are the used models, and we found that Quen3 4 billion is the best fit for our approach. Then we use Anthos plus GRPO training for fine-tuning this model using our knowledge. Then we fine-tune the model and optimize weights using LoRa adaptation. Then stored the database. Then stored the trained fine-tuned model in the Hugging Face. So here is the stored model. So we exported it in the GGF format. Then we use Olama for serving the model. So we installed Olama on EC2 instance, and using that EC2 instance, here we can see the model is running in our EC2 instance. We can run the model using Olama. So here we can see the model running. So the model is now running on the EC2 server. So likewise, we can host the model in the EC2 server. Then we use for the developer facing, we use VS Code extension. So users can select the code they written, and they can view the vulnerability report. So So that's the roadmap and the system architecture of our system. Then this is the data preprocessing pipeline. As I say, the preprocessing part is somewhat hard because they had a structure like this. And we did like in that we first extracted the functions from these folders. Then we balanced the dataset. Then we enriched the CW dataset with additional knowledge from open source databases. Then we cleaned and validated, and after finally we generated the final dataset and stored it in the Hugging Face Hub. So this is the final dataset we used. Then when it comes to challenges and limitations, the main challenge was resource constraints, and there were many issues with limited GPU resources. We use Colab and Kaggle platforms for training this model. So we mitigated that by actually incorporating Unswerve with LoRa. Then model selection, actually we tested many models and selected this final model. And also there was some issues with the Hugging Face transformer library. Actually we reported that into Hugging Face and they fixed it in the next version. So like here we can see they fixed it in their next version. Like after we reported it, they have fixed it in their next version. So that's our system architecture and the limitations we found in the limitations and challenges we face.
For the MLOps part, we have used MLflow tool. From here, we have tracked our experiments, different experiments, and recorded, tracked the different parameters in our training. So in here, we can compare the parameters, uh, outputs of different experiments as well. Also, uh, we have used the MLflow tool as internal model registry. In here, we have uploaded our different models resulted in different experiments. So in here also we can compare uh, those different models. So in summary, in MLOps part, we used MLflow tool to track our experiments and use as a model registry.